everyone. Thanks for coming to the seminar. Today, it is my great pleasure to introduce our speaker, Eleanor Hamilton. So Eleanor did her PhD at Cardiff University and currently is a postdoc at the University of Switzerland. And yeah, without further ado, please go ahead with the talk.
Thanks very much. Okay, so today I'm going to be talking about understanding precessing binary black hole systems.
Yeah, of course, there's always technical issues. I think possibly like coming off full screen and bringing back. Would be a trick. Or maybe you may even consider like unsharing and then sharing again.
That work?
So yeah, I think I will need to also share soon because right now it's done.
Yes,
plan.
Yeah, I was just checking it now. Where's the room? Is it sharing?
I think it's coming. So I can see a black screen for the moment. Should be.
Where is displayed the Zoom link? Because in the page of technical.
It's because we don't share it. It's for recording purposes. So I'm not yet seeing it on Zoom. And also, I think
is it there? I think it's there now.
Yes, it's there now. Thank you. It took a while.
Okay. Yeah. Okay. First, I will start with some introduction and background, recapping things you may already know about the LIGO detectors and recent observations, as sort of a motivation for the work I'm going to be talking about. Then I'll discuss the basics of waveform modeling, the techniques we use, the principles, and then give an introduction to the concept of precession as spin precession, spin-induced precession in binaries, and what this means and how we model it for our detectors. I'll then to talk about a new model we've made, which models these precessing spin binaries and some of the physical insights we've had in producing this model, learned about these systems, and then focus on one particular example of one of these insights and what this means for our detections. And other analysis that we perform with the LIGO data. Okay. So, as you may well know, we currently have a network of ground-based gravitational wave detectors. We have two in the US, Hanford and Livingston. All of these detectors operate on essentially the same principle in that they are microscopic interferometers with added aggregate. The two detectors in the US each have arm length of 4 kilometers. The one Virgo in Italy has 3 kilometer arm length, as does Paolo in Japan, and GW600 has just 600 meter arm length. There's a planned detector in India, but that's not yet defined and not yet able to contribute to gravitational wave observation. The arm length of these detectors, of order of a few kilometers, essentially puts them in the frequency bandwidth that enables us to detect gravitational waves from solar mass sources. So these are black holes or neutron stars in binaries, where the total mass of the binary ranges from a few solar masses up to a couple hundred solar masses. If you have a much longer arm length in your gravitational wave detector, then you're able to measure much heavier systems. We also need these very long arm lengths in order to have the sensitivities required to measure the gravitational waves. The advantages of having this network of gravitational waves detectors is both that we get a louder signal when we detect it, and that the having the multiple gravitational wave detectors enables us to break some of the degeneracies in our signals. So for example, in particular, if you have only a single gravitational wave detector at a given orientation, then it will measure only one gravitational wave polarization. Within general relativity, you have two gravitational wave polarizations, so you need at least two detectors in order to measure both these polarizations. And these two detectors must be in a different orientation. The two LIGO detectors, Hanford and Livingston, actually have the same orientation. And this is so that we basically measure a louder signal when the two detectors are both observing at the same time, which makes us more likely to detect the gravitational wave, but less able to determine the properties of the gravitational wave, of the system that has emitted the gravitational wave. So it's particularly important that we have Virgo at the moment, which is the one that contributes most to our detections, but also measuring these two gravitational wave polarizations is important. It helps us break the degeneracies that we see between some of the parameters of our models, properties of these binaries. So for example, it's very hard to disentangle the mass ratio of the binary. One object is heavier than the other from the spin properties of the binary. Measuring these two different polarizations enables us to do that better. So far we've had around a year and a half sort of continuous observing time with our gravitational wave detectors. The first part of this was just with the two LIGO detectors, and then the Virgo detector most recently, and CAGRA joined just at the end of the last observing run, but not really with any sensitivity that enables us to make any confidence statements. But so far we've been able to detect around 90 binaries. And we can see that the majority of these binaries sit here in this sort of the total mass binary above the side of the black hole, above the side of the dot, and it's here in the bands. This is what we sort of call our vanilla binary black holes. They have a mass ratio of close to 1, so each of the black holes in the pair, the initial black holes, have a very similar mass. And they're sort of between 10 and 50 solar masses. This is kind of interesting because you can see that these are much heavier than the sort of standard black holes that are detected with electromagnetic observations. And we're also starting to see a population of very heavy black holes, which are known as intermediate mass black holes, which are kind of interesting. We have these black holes here, these initial black holes, which lie in something called the pair instability supernova mass gap. No one knows how they form. They cannot be formed by standard stellar evolution processes. So the fact that we're starting to see a population there, very interesting from the astrophysical point of view. And these intermediate mass black holes also, they've not been detected previously. So already our gravitational wave detectors are building up a picture of the black holes in our universe that we don't have otherwise from existing electromagnetic detections. And we want to be able to add to this picture, describe better these populations. And to do this, we are going to need all the tools at our disposal. First, I'd particularly like to talk about just a small number of these detections that are of particular relevance to the type of systems that I study. The first of these, GW190412, contains a black hole of 23 solar masses and a much lighter object of 2.6 solar masses. And so the mass ratio of this system is 10. And this is the largest mass ratio that we've seen. And in this large mass ratio, this helps us decouple some of the properties that we try to measure with our detections. And in particular, it's much easier to detect whether black holes in populations are spinning if you have a large mass ratio. The degeneracy between the masses and the spins decoupled here. Particularly interesting for this system we didn't detect any evidence of spin. So this is one of the few systems where we've been able to make a conclusive statement about the properties of the black holes, and they weren't spinning. So that's interesting. But then we do also have another two observations where we have seen some spin. So the first is the GW190412. Also has an asymmetric mass ratio, has a mass ratio of about 3. This was the first system where we started to see the higher harmonics in the signal. So not just the dominant quadrupole term, but also the higher harmonic. And this higher harmonic also helps us detect the spin properties of the system. And you can see particularly from this plot that if we consider a gravitational wave signal model that just contains the dominant multipole, so it only contains the quadrupole and it doesn't allow the system to have any spin on the black hole, then we have very uncertain measurements in, say, the inclination and the distance to the binary. If we then make a model of the gravitational wave signal that includes more physics, so we allow for these higher harmonics and on top of the dominant multipole, then we remove this part of the detection entirely and focus entirely on this zone here. And then finally, if we add in the possibility of precession to our system, that would further reduce the error bars, even more definite statements about the properties of this. So it's very, very important in order to measure the properties of this binary and from this infer the astrophysical population of the black holes in the universe, that we have really accurate gravitational wave models that we're very confident in, and that include all the known physics that we possibly need. And the second example of the signal on the slide is another case where this is particularly important. And this is a more recent detection. Unfortunately, it's a sort of mass ratio 2 object. It's much harder to make conclusive statements about the properties of this signal. But it is very possibly the first detection we have of a precessing binary. So this is not just a binary where we have spins on the black hole, but this is where the spins on the black hole don't have to be aligned with the orbital angle. And this is sort of the more generic consideration, right? The fact that the black holes would have their spin aligned with the orbital angular momentum is a very sort of specific setup. But it's much easier to measure this aligned spin component. So it's much harder to make statements about the precession affects the existence of in-plane spins for the binary. So this is unfortunately not, some people think it's very definite that there is precession there. Some people are less convinced. There were data quality issues at the time. Some of the models that we have do indicate the existence of precession. Some of the models don't indicate the existence of precession. And all of these models it's right at the edge of the parameter space that they model accurately anyway. So we not necessarily completely trusting the results. And really this puts the emphasis, the motivation on why we need to make these better models. We need to make sure that we are ready for the next set of the next observing run within by Library Forever, which is due. Yeah.
So which of the models that are saying yes,
The names of the models.
No, well, yeah. So which models are the ones saying spin possible?
So of the models that we have available to us that include, so here, I think all of them, well, I don't think all of them say some spin, it's just a question of whether it's in plane or not in plane. And the one that has most information from numerical relativity that we expect to be most accurate for this kind of heavy mass system where we see the merger ring down part of the signal right in the bucket of the detector in the most sensitive part, that is the one that says there is precession. So that is sort of the biggest statement that there definitely is precession present here. And the other signals don't, the other models that don't involve numerical relativity and form precession effects, they don't really support the existence of precession.
What exactly are we seeing in that? What's on the axis?
This one.
Yeah.
I know it may be easier for people if we could also use the pointer one. Thank you.
This axis is inclination of the binary relative to the detector.
Okay.
And this axis is the distance to the binary and megaparsec.
But this is for one event, right? I mean,
Yeah. Yeah. So with gravitational wave detections, we have huge uncertainties in a lot of our parameters. Yeah, particularly the distance. The intrinsic
megaparsec, or
megaparsec.
like,
Yeah.
it's a bit hard to see them.
Sorry.
No problem.
Yeah, the intrinsic parameters of the binary, so the masses and spins, we measure much better. We have much narrower error bars. The extrinsic parameters, like distance and inclination, have really large error bars. And this is because they're very degenerate with other properties. So, yeah, I think particularly distance and inclination. So I'll get onto it in a minute, but most of the gravitational wave signal is emitted in a particular direction. And so if you look at a binary with your detector straight on, then the signal will be very loud. And if you look at it head on, then it will be very quiet. And so if you cannot well constrain the inclination, then you cannot constrain the distance because you don't know if it's face on or edge on.
Right.
And it's sort of removing this whole inclination part, including the additional physics in these models that help us better constrain and or tighten the error bars.
So the inclination is the most important variable that we can constrain distance and other properties in general.
The distance, definitely. I think, as I say, the extrinsic and intrinsic parameters decouple a bit. You can measure the intrinsic parameters without knowing the inclination. Okay.
Thanks.
Cool. Okay, so as I mentioned, we're now coming up to the next observing run. This will be 04. It starts in about 2 months. And during this observing run, in the gap between the last one and this one, they've been massively upgrading the detectors. So the sensitivity of these detectors jump up, particularly LIGO, but also LIGO, and we will start to have hydro contributing much more meaningfully to the detector. And something that should be remembered is that as the observable volume of the universe scales sort of as the cube of the increase of the distance, and this distance goes with the sensitivity. So we're going to be sensitive to a much, much larger volume of the universe. And so we've seen, order 100 detections so far. During the next observing run, we should see order thousands. And so, this poses a sort of technological challenge in terms of the data analysis, but it also means, whereas we've so far had a handful of events that we consider particularly interesting, ones that have high mass ratios, ones that might have spins, we now should really start to build up a population of these events, as well as see ones that are even sort of more extreme than the ones we've seen before. So we need to be ready with our gravitational wave model in order to encounter these events, make sure that we have accurate models up to high mass ratios, have models that we trust in terms of the precession effects, the spins, and make sure also, again, that we have multiple models that we trust that do these things, because we need to look for any systematics in our models. And as we've already seen, we're already seeing detections where models start to disagree, and then we need to decide what do we trust most, what is really the informative thing. Okay, we've already made quite an argument for why it's important to have accurate gravitational wave models. But essentially, to recap, we use these gravitational wave models to infer the properties of the binary. We do this by, we build up a template bank that essentially contains all the models. And then when we get a signal in, we compare it to the gravitational wave model with a given set of properties, and we find the properties of the model that produce a signal that match best with our detection. And that tells us the properties of the binary that produce this signal. Once we have an accurate picture of the properties of these binaries, we can use it to build up an astrophysical population model. So here, for example, you can see the vanilla BBH population that I was talking about earlier, which have a sort of, equal mass with the primary and secondary being sort of tens of solar masses. We can also see that the outliers in terms of the binary neutron star or neutron star black hole systems, and again at the other end, these intermediate mass black holes, and down here the ones that have a high mass ratio away from 2 = 1 line. And then finally, on a sort of separate note, we need our models to be accurate, not only so that we confidently infer the population of the black holes, but also because we do use these models to test for deviations from general relativity. And so if it turns out that our models don't capture the right physics or there are any systematics in there, then we could sort of incorrectly see deviations from general relativity that we don't understand the origin of. At the moment, with the sensitivity of our detections, if we do see deviations, we are much more likely to assume that they come from model systematics than from any deviations from GR. But it is better to know what those systematics are in advance rather than have to work them out sort of on the fly. So in order to build our gravitational wave models, we use a number of different techniques. The analytic ones are in blue and the numerical technique red here. First and foremost, we have post-Newtonian theory, which is a perturbative approach where you have the gravitational waves treated as a perturbation on the flat space-time. You perform an expansion in the parameter V over C, and this means that it's appropriate for a weak field and a system where your source is slow moving. And so this post-Newtonian theory approach is only appropriate during the inspiral stage of the binary, when the two black holes are very far apart and the gravitational wave field is weaker and they are moving much more slowly. We then have the effective one body theory, which sort of extends the post-Newtonian theory. It uses a resummation process that means you can really push this approach right up to merger. But unfortunately, it's not it cannot be extended completely through merger, and we still need information for numerical relativity during the merger and ring down in order to properly inform our models there. And then finally, we can perturbation theory of a Kerr black hole in the ring down to see the single remnant black hole, how it decays through the emission. And we use all of these techniques together in order to make the complete inspiral merger ring down models that we use for ground-based systems, stellar mass source black holes. Other techniques are used for, say, extreme mass ratio binaries and so on that will be seen by other detectors such as these. So the existing gravitational wave models can be divided into three broad categories. The SCOB family, the Phenom family, and the NR surrogate family. The SCOB and Phenom family both follow the same broad approach to gravitational wave modeling. They use an analytic description during the inspiral that comes from post-Newtonian or effective one-body theory. They then take information from numerical relativity to tune some of these parameters that come from these theories during merger and ring down. So for example, you'll take the functional form of the gravitational wave that is predicted by post-Newtonian theory, but instead of using the values of the coefficients in that form, you change them instead, and you produce a large number of numerical relativity simulations across your parameter space and make a fit through the coefficients of this ansatz across your parameter space and use that instead to inform what the values should actually be, and then connect it through to the perturbation theory numerical results at the end. The NR surrogate family uses a completely different approach, where they instead produce thousands of numerical waveforms across the parameter space that they wish to make a model for, and they then interpolate between each of these models purely numerically with no analytical information. And this approach is therefore extremely accurate. It inherits only the errors that could be present in your numerical data, but it's unfortunately limited because our numerical simulations incur errors as they evolve. And so the longer the simulation, the increase in the dephasing error that you'll have as you evolve it forward. So they are the NR surrogate family is only applicable to sort of these very heavy mass systems where the signal that is present in our detector will be there for a short period of time. The other difference between the models is that some are produced in the time domain, where we sample the gravitational wave signal at a set of time, the other in the frequency domain. The advantage, obviously, of the time domain is it's sort of the native domain in which the numerical data is produced, or the analytic theory produces its results. But the gravitational wave data analysis, the comparing of the signal to the model, that's done in the frequency domain. And so in order to have a model that is sufficiently fast, in order to use it for analysis of order of thousands of events, it's often more advantageous to go into the frequency domain in order to produce your modeling, which then also happens. Okay, so to date, these models that I've listed here are specifically the models that were used during the last observing run for the most recent gravitational wave analysis that we've done. And all of them now include information about the higher harmonics, the subdominant effects on top of this strain, and all of them include that information and have calibrated it to numerical relativity simulations. So they are well informed by these, by the numerical data that we have. These models also all include information about precession in the system, but unfortunately, only the NR surrogate model has used numerical data in order to inform those effects. And so the other models, particularly looking at merger and ring down, you do not necessarily want to trust the information you're getting about the precession effects from. And this is partly because these are higher order effects. First and foremost, you want to get the dominant signal right, then you move on to the higher order effects. And so we're still sort of moving through this process. And what I will be presenting today is an extension of the phenom family of models to include numerical relativity information about precession. So exactly what is precession? As a brief recap, as I said earlier, you have the power emitted in the gravitational wave. The dominant amount of power is emitted perpendicular to the plane of the binary. And this is what forms what we call the 2-2 mode or the quadrupole mode. And for a non-precessing binary, one where it's not spinning or the spin is aligned with that orbital angular momentum, this 2-2 mode is what dominates. And essentially we get the modes when we decompose in a sphere, in a fixed frame around our frame. For a precessing system, instead, we now have spins on the black hole that are not aligned with the orbital angular momentum. Spins that are aligned with the orbital angular momentum produce something called the hang-up effect. In the case where they are sort of positively aligned, then the total angular momentum of the system is greater, It will therefore take longer to be radiated away, and the binary will take longer to coalesce. In the case where they're anti-aligned, then the total angular momentum is reduced, and the binary will coalesce sooner. In the case where they're not aligned with the orbital angular momentum, then you get a coupling effect, and this causes the plane of the binary to precess, as shown here. And that then means that the power, if you're still decomposing your gravitational wave signal on a sphere in a fixed frame, the power is now spread out amongst all the modes, the higher harmonics, and we no longer have a nice clean signal in order to model. And this is what's shown on the left hand of this plot. You can see that all your different modes, they have oscillations. The higher harmonic modes, the 2, 0, 2, 1, 2, -1, they have even more power than what should be your dominant mode. And this makes modeling this gravitational wave signal almost impossible. It's a nightmare. And so what we do instead is that we transform to a non-inertial frame. And in this non-inertial frame, we track the precession of the binary. And so we can do this in two ways. So we can either track the precession of the orbital angular momentum, the Newtonian orbital angular momentum, which will track the orbital plane, or we can track the dominant power emission and transform into a frame in which that dominant power is always emitted in the 2, 2 and the 2 minus 2 modes. And what we get when we transform into this frame, known as the co-precessing frame, is the waveform on the right, which looks very much like an aligned spin waveform. And in fact, we can make a mapping from a precessing binary to the same aligned spin binary and just use that waveform, except for in the ring down, where we have to adjust for the final black hole, which will have a different final massive spin to the equivalent aligned spin binary, and this will therefore affect the quasi-normal modes for the group. But apart from that, we can now just model this system. Okay, and so this transformation from the co-precessing frame to the inertial frame and vice versa is described by these three Euler angles, alpha, beta, and gamma. Where here B is, say, the maximum emission direction, the direction in which the majority of the power is emitted, and alpha and beta describe the precession of this direction, and then gamma is defined by the minimal rotation condition, and this is just to enforce that inconsistencies between the frames. So, in order to make our final precessing model, we essentially end up with two components. We have to model the waveform in the co-precessing frame, where it looks like an aligned spin binary, and we have to model the frequency-dependent angle rotation in order to go from the inertial to the co-precessing frame and back again. And that's what produces our complete waveform. So, okay, onto this waveform model, produced using these techniques. So first of all, this model has been tuned to numerical relativity. We've used numerical relativity to inform the precessing information in the system. In order to do this, we had to produce an entirely new catalog of precessing numerical simulations. This catalog covers the parameter space up to Q8 and spin 0.8 with various inclination angles of the spin. These systems are only single spin systems, so the spin is just placed on the heavier black hole. We don't consider even more dominant effects which come into play when you have two spins on both your black holes. And the waveform generally have a starting frequency in this range, which means that we end up with around 10 orbits before merger in our signals, which is enough time, is a long enough signal mostly to connect smoothly to the analytic perturbation theory, PN, or effective on body results prior to merger. And this catalog, should anyone wish to take a look at it, is now publicly available for use. All the dynamical information as well as the waveform information. Okay. This is an example of one of the waveforms that we've modeled, the co-precessing frame waveform. where the amplitude of the dominant multiple is taken as a nice feature, no oscillations induced due to the precession, and the phase derivative is shown here, and this also follows the sort of non-precessing phenomenology. And here, for example, this the dashed line here, so the grey line shows the numerical data, the dashed line shows what happens if you don't introduce this information from numerical relativity, you just make the naive approximation that you can exactly map to an aligned spin waveform. And you see that you get a slight sort of disagreement during merger-ringdown that we've adjusted for as informed by our numerical data. The most important thing, though, to notice is that this dip, the location of this minimum, is in a different place if you don't consider the effect of the co-precessing frame correctly. And this dip is what corresponds to the ring-down frequency. So before looking at this numerical data, the precessing models were in fact incorrectly predicting the ring-down frequency of the binary. And this is because when we transform into the co-precessing frame, we shift the ring-down frequency. And so the results from perturbation theory, the quasi-normal modes that are derived there, are only strictly applicable to binaries in the frame in which the final spin is aligned with the z direction. And we get this shift we get this shift when we were coming in, but we were applying the results in the wrong frame, and so when we rotated back into the inertial frame, we were getting the value of the ring frequency incorrect. We then need to model the precession angles that go from one frame to the other. We can see here a comparison. The MSA is a type of post-Newtonian expression for the angle, stands for multi-scale analysis. You can see here that for one of the angles, the post-Newtonian expression agrees pretty well with the numerical data, all until you get to the merger, at which point it would be a dip, which the post-Newtonian expression is not predicting. But for the other angle, the post-Newtonian expression is already off in the amplitude long before our numerical data starts. And so we've had to make rescaling adjustments here. And then it does not predict this turnover, this drop in the angle that we have now correctly modeled using the numerical data. And these neglecting to model these effects properly, they do have impacts on the physical parameters of our signal. And we lose information about the physics. I did mention that we use a single spin mapping. We tuned our numerical data only to single spin simulations. We of course need a model that describes two spin simulations. And so we extended this using a single spin mapping. And here, for example, we compare to a numerical simulation in which we have both spins. And we can see that if it doesn't agree quite so well as it does in the cases where we've tuned to our data, we're clearly capturing again the features, these oscillations in the angle that come in during an inspiral, but fade away at merger, and we still have this sort of drop off that we've included in them. The model performs a lot better if we do something called the match, which is basically the noise weighted inner product between our numerical data and our waveform model. We're no longer seeing these worse matches that are up here that could negatively influence our parameter estimation. And we're starting to see a lot more that are much lower. So we have improved confidence in our ability to detect and analyze these signals. And then finally, the physical observations that we introduced. As I said, the beta drops rapidly during match, And this rapid drop is not described through either post-Newtonian theory or from perturbation theory. It's purely a merger effect. And so this is something that we were unaware of before we formed this study. And this drop itself has an effect on the waveform that you can see here, where each of the higher harmonics, in fact, turn over at a slightly different frequency. And this is what's being captured by this drop. If we don't have this drop in beta, then we see that they just all turn over at exactly the same frequency. We can also see that at lower frequencies, where the amplitude of this angle was being incorrectly modeled by the Newtonian theory, the amplitude of the higher harmonics were incorrect. Essentially, because this model measures the ratio of the higher harmonics in the frame. Did you say 10 minutes? 5 minutes.
Well, now there's 5 left.
So I briefly just wanted to go over this effective ring-down frequency, the shift in the ring-down frequency as we go into the co-precessing frame. I'm sure many people may be familiar with quasi-normal modes, which are excited when you have the remnant binary formed by the merger of the two initial binaries. Essentially, the perturbation that you get when two black holes collide can be either aligned with the spin of the final black hole, or the perturbation can be anti-aligned with the spin of the final black hole. And in the aligned case, we call it the prograde frequencies are excited, and in the anti-aligned case, retrograde frequencies are excited. But in the case of precession, then things are not so simple, and we no longer have the perturbation either aligned or anti-aligned. It is instead inclined relative to the final spin. And this means that we don't know. It is much harder to predict whether the prograde frequencies or the retrograde frequencies will be dominant. Both will be excited. And so we can see here that from looking again at our numerical simulations, both frequencies are excited, and we get a superposition which causes an oscillation in the final frequency of the frequency of the gravitational wave that is emitted by the final remnant black hole. But the mean of this oscillation will essentially be either the prograde or the retrograde frequency, depending on which is excited most strongly, depending on which is dominant. And the amplitudes of these quasi-normal mode frequencies are not given to perturbation theory. And so we don't know which dominates naively. This is what we see in the inertial frame. We see a sharp discontinuity, and this is essentially when we change from the prograde frequency to the retrograde frequency dominated. And it's this exact transition point that we are unable to determine in theory. But essentially, we found from our numerical data that when this precession angle beta passes through pi/2, this is when we transition from the prograde to the retrograde. And it's this pass, the existence of this angle even for the ring down component is slightly odd, because how do you even define precession when you only have the one system? But if we define precession as tracking this optimal emission direction, the direction in which the majority of the power of the binary is emitted, then we still find that it's not aligned with the final spin. And using this angle, we can predict whether the prograde or the retrograde frequencies dominate. So I just wanted to recap what these angles are here. Oh, sorry. And so, yes, we can come up with an analytic theory based on the rotation between the frames that gives us the correct value of the ring down frequency in the co-precessing frame. And from this, we can infer that when this term vanishes, that is the very point at which we transition from the prograde to the retrograde frequency. And it's the point where in the co-precessing frame the values of the prograde and the retrograde frequency of it. And essentially, if we look at the result of this formula and compare it to our numerical data, which is shown here in the black crosses, then we get a nice smooth transition in the co-precessing frame. We no longer see this abrupt discontinuity, and we've come up with a description of the behavior of this ring down system in that frame, which is then very useful to feed back into our modeling and removes any waveform systematic effects that we might see. And in particular, as you'll know, this is really important because these quasi-normal mode frequencies are defined by the mass and the spin of the remnant black hole. And so if we get the ring down frequency of the system in our model wrong, then we will incorrectly infer the mass and spin of the remnant black hole. And one of the tests that we perform within LIGO is known as the inspiral-merger-ringdown consistency test, where we infer the properties of the system during inspiral from the gravitational wave model, and then we infer the properties separately during merger and ring down using the results from perturbation theory, again with our models, and then we check that they give the same prediction and that the signals that we're detecting are consistent with our understanding of general relativity. And so if we have the ring down frequency wrong, we can potentially incorrectly infer deviations from general relativity. So far, we haven't seen any signals with properties where we'd worry about this, but again, going into the next observing run, we really hope that we do. Okay, so thanks very much.
Very good timing indeed. Thank you very much. So do we have questions from speaker?
I have just one question. We can come back to the slide number 10. Just out of curiosity.
Yeah.
So, if I understood well, you said that the effective non-body is an approach which extends a bit the post-neutrino theory. And
Well,
I think you said with a sort of resummation.
yeah.
What kind of resummation is?
Yeah. So, I mean, effective one body applies the, like if you have Newtonian relativity and you can transform your variables into, from a two-body problem into a one-body problem, essentially. It applies the same sort of approach within GR. And then you get a theory and you use something that you call Pade resummation. But I couldn't explain to you the details of that process, okay. I'm afraid. But essentially to renormalize the infinities that crop up in that theory.
Okay.
The usual comment is that there is more physics involved into the one body descriptions, because like they are able to indeed, as Eleanor was saying, to describe it as a one body system to a two body system, and they're also able to go like even this they were saying that they could go through merger, but
they can go through merger. The theory extends through merger, but it's just not accurate. So you use the ansatz, the form from the effective one body, but then you have to use numerical relativity to inform.
So, just out of curiosity, why is it called post-Newtonian? I mean, it's GR, right?
Post-Newtonian, I guess, because you essentially take a flat space-time,
right,
and then expand in V over C. So you can reduce GR in the limit of low V over C. If you take the first order term, then you get the Newtonian limit.
Right, and you can do this in the first state of the merger because it's V over C is small, or?
In the first state of the merger.
Or because you said the early inspiral state. So
yeah. Yes. Yeah. So V over C is small during early inspiral.
Is early inspiral the first? What is the first state of the merger? Or is it...
No. So we have inspiral where the black holes are very far apart.
Right.
And then late inspiral they're sort of close together. Merger is when.
Okay. That's already. And another question was, okay, so this is, so I would say the main of this work is all understanding on how these binary systems work and understanding. We look at these detections, how can we draw conclusions to the parameters of these systems, right? But if we take a step further back, look onto this field of research, right? Is the idea to test GR? Is the idea to I mean, first of all, it's really amazing that this is possible now. It's not so long ago that we made the first rotational wave observation. But what's the bigger goal for science in this field? What would you say? Like, what is it? Understanding these systems and these parameters, or testing GR?
I think it depends where in the field you sit.
Yeah.
For some people, we've very much reached the stage of gravitational wave astronomy, where this is now about making observations, recording the properties, building up a picture of what's out there.
Right.
And maybe looking for objects that we don't predict to exist, and that will open up a new field. In terms of testing general relativity, for some people that's definitely the end goal. It's not a goal that will be achieved by ground-based detectors. We do not have the sensitivities, unless we really will see a huge deviation from GR that we somehow missed elsewhere.
This would be something for LISA, or?
So there are some things like echoes that people do have hopes of seeing with LISA.
Yeah.
Again, you know, with LISA, we get much better sensitivities, and so that will enable us to probe GR. But we also, again, will see orders of magnitude more detections, and with that comes problems like overlapping signals, and when you observe two binaries at the same time or more. And this will introduce sort of much more complicated data analysis problems, detangling things, and will these detangling methods enable us to see deviations from GR? It's still uncertain exactly at what stage we'll really start to be able to probe general relativity with these detectors.
Yeah, thanks.
Do you have more questions?
In this slide, where you introduced, as you mentioned, from the commercial to the precession. Yeah, exactly.
This one? The previous one.
Yeah, this one.
Yeah.
So when you look at that map, it's really remarkable, right? That the purple line afterwards looks so simple. But in the other two distances, like if I had to model the other two curves, I would also say that that was a nightmare. Why is it not?
These ones.
Yeah.
Yeah. And this one, noise. Don't trust the green,
Okay.
the green curve. But yeah, I mean,
Particularly early on, right?
yeah, I mean, again, at what point do we probably don't want to get all the gist, but these sort of observations. Yes, I think that.
So is that are those features actually modeled?
No, not in our current model.
So it's almost just like a straight line.
Yeah, I think if you looked at an aligned thing, that it's going to be flat, basically. And so those are further perturbations on top of the ones we're already on there. And yeah, they're not included yet.
Okay, 2 minutes. Do you have more questions?
Your expectation. What's your expectation of all these models being uniform field and say these will, but there hope that we'll have enough models by then.
So
Even all these already out.
for the ground-based detectors, yes. And I think partly this is because the surrogate model will probably take over. And so there are a number of different techniques that can be used to extend them to be applicable to lower mass ratio binaries. And also we might take techniques used to create those numerical, the surrogates, where we make much more densely sampled parameter space, and we still use our analytically informed ansatz, but essentially use a sort of algorithm to get the coefficients. And so we have long binaries that are extremely accurately modeled. There's still physicals that are missing from the existence. We don't have eccentric binaries. We don't have hyperbolic flyby encounters. But I think by cosmic explorer and ET, yes. LISA is a whole other issue where they are different systems, different techniques need to be used to model them, and we're definitely not ready, and whether we will be. I mean, I hope so, but the other problem is our numerical relativity codes are not accurate enough for LISA. So that's got to be solved before anything.
Any more last questions? No, let's thank the speaker again.
If you enjoyed the video, like and subscribe.